Yes, good morning. Again, there is a topic Cauchy sequence, and there are some more theorems based on this topic. Let's start doing that. This is a very important theorem. If Kn is a sequence of compact sets in a metric space X such that Kn contains Kn plus 1, n belonging to natural number, and if limit n tends to infinity, diameter of Kn equal to 0, then intersections of all the Kns consist of exactly one point. Kn contains Kn plus 1 means if you put n equal to 1, we will get Kn contains K2, or K2 is a subset of K1. Let's see the diagram. See, this is your K1 and this is your K2, this is K3 and so on. For this condition, this K1 contains K2, then K2 contains K3 and so on, right? So K1 is a bigger set, a compact set. We have also given that diameter for this Kn when n tends to infinity equal to 0, and we have to prove that their intersection consists of exactly one point. What is the intersection of all these Kns? What is the intersection for K1, K2, K3? Only this part, right? And if we move further on up to Kns, the intersection will be very, very, very far away, right? Now, first of all, for this proof, we will prove that intersection of all these Kns is non-empty. What are the Kns? That is the compact set. First, we have to prove that intersections of the compact set is non-empty. This result I have proved in my course Real Analysis Part 1. In that I have proved this result in the topic compact sets. You can check over my course 1, the real part, the part 1 for the real analysis, right? You can check the proof in that first part of real analysis. And after proving this result, let's move further on to prove this theorem. We will do this theorem by the contradiction method. Let's take this intersection of Kns to be equal to K, right? And what it is given that diameter for this Kn where n tends to infinity limit is there equal to 0. And I have taken all these intersections to be equal to K. If possible, suppose, now we have to prove that this K consists of exactly one point. So if possible, suppose K contains more than one point. Right? Then what we can say about the diameter of K? This diameter of K will be positive because this K contains not one point but more than one point, and distance between the point is positive then, right? So I have taken this diameter of K to be greater than 0 because distance between 2 points can be as small as possible or it can be a positive distance. Hence the diameter of K is positive. Now since this K, which is the intersections of the compact sets, this Kn is contained in, this intersections of Kn is contained in K. Kn. How? See? If we see the intersections for only 3 compact sets, K1, K2, K3, what is their intersection? And going from 1 to 3, what is their intersection? K3, right? And this K3 is a subset of K3, It is also the subset of K2. It is also the subset of K1, right? So K3 itself is a subset of K3 or K2 or K1, or we can say that this K3 is a subset of if we take n to be 1, then K1 is a subset of K1. If we take n to be 2, then K2 is a subset of K2 and K1. If n is 3, then K3 is a subset of K3, K2 and K1. So if it is n, then this intersection is a subset of Kn. So all these intersections of Kns is a subset of their bigger sets. Hence, I have written this intersections of Kn is a subset of Kn. Then what do we say from this? Which implies the diameter of K is a subset of Kn. Therefore, K is a subset of Kn. And from here, I can write diameter of K is less than equal to diameter of Kn, right? And what can we say about diameter of Kn? This diameter of K, this is positive, right? So I'm writing like this. Diameter of Kn is greater than equal to diameter of K, and this diameter of K is further positive. We have mentioned here because this K contains more than 1 point, so their diameter is positive. Now taking the limits all over this, taking limit n tends to infinity, diameter Kn greater than equal to diameter. Since limit is on n, so here only limit n tends to infinity I should write. Here I should not write because here it is only K. This is strictly greater than 0, which implies this limit n tends to infinity, diameter of Kn is all positive, right? Now this is a contradiction. Why? Because it is given that this diameter of Kn, limit n tends to infinity, is 0, right? But here we are saying that this limit diameter Kn is positive, which is a contradiction. Hence our supposition was wrong. Therefore, our supposition was wrong. What we have supposed? That their intersection contained more than 1 point. This supposition is wrong. That means this intersection contains exactly 1 point. Thus, K equal to, which is taken as intersections of all Kn's, consist of exactly 1 point. Right? Easy? Right. The next theorem. In any metric space, every convergent sequence is a Cauchy sequence. Now metric space is given, it can be any, and every convergent sequence. So there is a convergent sequence in a metric space, and that sequence is a Cauchy sequence. This we have to prove. So a convergent sequence in a metric space is given to us. So let Pn, this be a convergent sequence in a metric space X. I'm writing MS for the metric space. And suppose as it is a convergent sequence, it must converge to a point. So let Pn is converging to point P. Now the definition for the convergence sequence. Then for given epsilon positive, there exists a positive integer n such that the distance of this Pn with P is strictly less than epsilon, but I am taking epsilon by 2, right? For n greater than equal to, and you can guess your epsilon to be any real number. So now for proving the sequence to be a Cauchy sequence, I must define my distance of any two terms. Now when the sequence will be a Cauchy sequence? When the distance between any two terms of the sequence can be made as small as possible, or which is strictly less than epsilon. This I have to prove. Now can I write this distance as this is less than equal to distance of Pn with P plus distance of P with Pm, right? Now for convergence sequence, this distance is strictly less than epsilon. So dP and P is strictly less than epsilon. Similarly, dP with Pm is also strictly less than epsilon. This Pn will be any term of the sequence, and this Pm will be any another term of this convergence sequence, right? Because this Pn, distance of Pn with P strictly less than epsilon by 2 is for n greater than equal to n, that is for P1, P2, P3, P4. Any term of the sequence, this result is true. So for Pn I am also writing epsilon by 2. For other term Pm with P, I am also writing epsilon by 2. And this is nothing but their sum is epsilon. For this dP and P, I should write n greater than equal to n. For this, I should write m greater than equal to n. So together I write nm greater than equal to n. This is nothing but the definition for the Cauchy sequence. dPn Pm strictly less than epsilon for nm greater than equal to n. This is nothing but the definition for the Cauchy sequence. Hence, Pn is a Cauchy sequence. So, but epsilon was arbitrary. Therefore, this Pn is a Cauchy sequence. Right? So in any metric space, every convergence sequence is a Cauchy sequence, but converse need not be true. That is, in any metric space X, Cauchy sequence need not be a convergent sequence. Let's check some examples. There is a remark. The converse of above theorem is not true. That is, a Cauchy sequence need not be a convergent sequence. That means if a Cauchy sequence is given to you in a metric space, then it need not be or may not be convergent to a point which belongs to that metric space. For example, if I am having the sequence 1, 1.4, 1.41, 1.414, so on, this is a Cauchy sequence in a metric space Q. Q is a set of rational numbers. Why this sequence is Cauchy sequence? Because in a Cauchy sequence, the difference between the two terms of the sequence can be made as small as possible. But this sequence is converging to root 2, right? This is nothing but the value for the root 2. So it is converging to root 2. But this root 2 is not belonging to the set of rational numbers. So the sequence is converging to a point, but that point does not belong to that metric space. And the metric space is a set of rational numbers. So Cauchy sequence of rational numbers does not converge over Q. One more example, 1 plus 1 by n to the power n. This is a Cauchy sequence in Q which fails to converge over Q. Why? Because if we take limit n tends to infinity over this is nothing but e. Do you remember? This is e, exponential. This e does not belong to a rational number. This e is not your rational number. So here also Cauchy sequence fails to converge over Q. Give examples of two Cauchy sequence of rational numbers which converge to irrational numbers. So I have to give an example for Cauchy sequence of rational numbers which is converging to irrational number. So what is the example? If I consider the sequence 1, 1.4, 1.41, 1.414, 1.4142, this is a Cauchy sequence of rational numbers, right? But where this sequence is converging to? If you move further on, n tends to infinity, where this sequence is converging to? This sequence is converging to root 2, right? This sequence is converging to root 2, which is not a rational number, which is a irrational number. Which is an irrational number. So I got a sequence of rational numbers which is converging to irrational number root 2. One more example, you can take the sequence as 1, 1.7, 1.73, 1.732, so on. This is also a Cauchy sequence of rational numbers. Now where this sequence is converging to? Yes, come on. Yes. This sequence is converging to? Very good. Root 3. Which is again not a rational number, which is an irrational number, right? So in a given metric space or in any metric space, Cauchy sequence need not be convergent sequence. Give examples of two Cauchy sequence of irrational numbers. Yes, now we are taking the example of Cauchy sequence for irrational numbers which converges to rational numbers. Let's take an example. Consider the sequence root 2 minus 1, then root 2 minus 1.4, then root 2 minus 1.41, root 2 minus 1.414, so on. This is a Cauchy sequence of irrational numbers, right? This is a Cauchy sequence of irrational numbers. Now where this sequence is converging to? If you take your limit n to be infinity, further on you move, this root 2 minus 1.414. See, here the difference is some real number, here the difference is some real number. But if you move further on, up to n tends to infinity, this difference will be very nearer to 0 or approximately tending to 0. So this sequence is converging to 0. So this sequence is converging to 0, right? And 0 is not a irrational number. 0 is a rational number, right? 0 is a rational number. Can you guess one more example? All right, we should take the example for root 3. Yes, root 3 minus 1, then root 3 minus 1.7, then root 3 minus 1.73, then root 3 minus 1.732, so on. This is also a Cauchy sequence of irrational numbers. We can make sequence of our choice. This sequence is converging to again. Yes, of course, this sequence is also converging to 0, and 0 is rational number. So we have found a sequence of irrational numbers which is converging to a rational number, right? Good. So next time some more theorems are there on the Cauchy sequences. Hope so. It's very clear to you. So very important theorems are coming in my next video. So keep watching and enjoy your day and have very blessing day. Goodbye.